have a filtration FT. Okay, so kind of define the stochastic integral for a class of function. So let's quickly recall over the description of the class. So imagine I have filtration. Okay, so this filtration is not necessarily generated by Brownian motion, but it's a kind of a filtration. That's what we are assuming, that this filtration is kind of a filtration to which the process of Brownian motion is adapted actually. Okay, that's first thing. Second is that if you take the increments of the Brownian motion, they are independent of say Fs, for example, okay, for all s less than or equal. Keep one thing in head here. I'm not assuming that f is generated by Brownian motion. Could be any kind of filtration, okay, that has two properties. Obviously, a particular manifestation of it is going to be the filtration generated by Brownian motion instead of it. Take it. And then we said that M2 telegraphic M2 R L2AD is the space of stochastic processes. Okay, it's a space of continuous time stochastic processes. So it has key properties. So what are the key properties of this? Those stochastic processes which satisfy, we are collecting in M2AD, is that this Ft omega is adapted. Okay, the same filtration, to which the Brownian motion is adapted. Okay, and the second thing is that if you compute the Riemann integral of expectation of f square of t, dt, it turns out to be finite actually. Okay, so these are the two conditions that satisfy. And also talked about that. If you see from the Bansky book actually, the stochastic calculus for finance, then defines as is defined as those processes which satisfy this condition. Okay. But rather than the Riemann integral of the conditional expectation, Riemann integral of expectation is finite, you have expectation of the Riemann integral is finite actually. You almost okay. Which can be achieved easily. If you see that we are in the assumptions of Fubini theorem, okay. So you can pull this expectation out because expectation is nothing, just integral with respect to the probability measure, underlying probability measure. Okay, so it's just one way, two ways to describe the same thing. And then what we tried to do, so what we said that if I have so the next was that if we say that if I have a step process, okay, that looks like this, equal to 1 to n, say xi I times ti minus 1 to ti, where obviously, this ti to ti minus 1 is the partition. Okay. Is the partition of this interval, right? In other words, it's a kind of a map that each instant in one of these subintervals takes a value xi minus 1 times, if I be more precise, okay, xi minus 1 times, 1 or 0 depending on the instant is in this subinterval or not actually, okay? And we also assume about xi minus 1 that it's fti minus 1 measurable. Then, what our task was to define, to take an f that is an arbitrary element from the L to AD or M2, what would be the meaning of, say, integrating, a trajectory of this process with respect to the trajectory of the Brownian motion from A to B, okay, for each omega in general. And for that, we actually had the same approach that we have in our previous case, that we proved an approximation lemma. We saw an approximation lemma. So we said, if I have an f that is from L to AD, but in addition it satisfies this condition that expectation of the, expectation of the f of t, f of s is basically a continuous function. So in other words, it's kind of a process that is adopted and for which this guy holds, and in addition, its expectation f of t, f of s is continuous, okay, where s and t are two instants. Then I can find a sequence of such stopping, such step processes, okay. So I can find fn's of star type, okay, of star type, such that yes, but okay, fn of star type such that fn converges to f, okay, in this manner actually, okay. So in really this manner, okay. So in L2AD manner. That's what we proved. Okay. And if you remember, what was the key thing that allowed us to get this result was that if you compute fn at an instant t, that t lies in, say, one of the sub-intervals, then the value of it is going to be that you compute the f at the left endpoint of, okay, left endpoint of the sub-interval, okay, and give this value on entire interval for each instant in t minus 1 and t. Okay. Now, and then we show that fn indeed converges to f, and it satisfies this crucial condition. Then I give you to read it for yourself. The next case is, this was just one case actually that, so obviously our task is to define the integral for arbitrary effect. Okay. The other case was, I hope you have read it, if not you should read it, is that when f is from L to AD and bounded actually. Okay. Then argument roughly goes like that. Okay, you can see that argument in detail. Then I can find a sequence, okay, of the processes in L to AD that satisfy this condition now. They are not the step processes, but they are the processes that satisfy this condition for which the expectation of f of t and f of s is continuous. Then such that fn converges to f in this L to AD sense. Okay, that's it. And then the third case and the generic case, okay, was that if I have an arbitrary element in L to AD, how can I approximate it? Okay. Then you can read up the proof, and it says that you can find a sequence of processes that are bounded actually. So each term in this is bounded. So in other words, the new case has been proved using the previous case actually, such that fn is a sequence of bounded sequence, such that obviously fn should be in L to AD, and fn converges to f in L to AD sense. Okay. So in other words, this is simply like that, we kind of prove the approximation lemma, that you can always find a sequence of suitable processes that converges to f in L2 AD. And then what we did, okay, I'm going into the details because otherwise, it will be blank actually, that what the heck is going on. Okay? And then we said that, okay, take an arbitrary stochastic, step process, for example, of this form and try to define, the integral, okay, the stochastic integral for such kind of a step process actually, where f is a step process. And how did we define it? We defined it that, okay, you take the same random variable exact I minus 1 and multiply it with the increment of the Brownian motion over that interval actually, where I goes from 1 to n. Okay, I goes from 1 to n. And then we also showed that this I is going to satisfy a linearity property, and it's also satisfy this function property that if I compute the expectation of the integral, stochastic integral of a step process, and it's a square, it's the same as computing the expectation of the square of t and dt. Okay, really like the etoism actually. So this is like L2 omega norm, and this is roughly like L2 AD norm. Okay, I'm not assuming at the moment that L2 AD has a topological structure, but you can prove it that it does have a topological structure actually. It does have a norm with it. Okay? And then we proved that if you take, for example, an arbitrary step process from L to AD, then what would be the meaning of the stochastic integral of it? Approximation lemma guarantees that I can find some suitable sequence of the process that converges to f in L2, that approximates f in L2 AD sense in suitable manner. Okay? And for these, I have a well-defined notion of stochastic integral. And then we say that, okay, this sequence of the stochastic integral of fn's, okay, converges. And whatever it converges, we gave that limit, in other words, that limit and goes to infinity in L2 omega sense, a name is a to b of t, dw of t actually. Okay? That was really the recipe of defining it. You can ask that, okay, so this is well defined in all senses actually. I mean, one of the things is that, okay, if f is in case 1, okay, if f is in case 1, then I can find the sequence of step processes that that satisfies this. If f is from say case 2 actually, so it's a bounded function actually, then I can find a sequence of such kind of a process. Okay. And you can always ask, you can think that basically that, okay, if f is bounded, then fn's are no more going to be a step process actually. They are going to be, what do you say, such kind of process for which this is continuous. But each such kind of element in this sequence can be approximated by a step process. Okay? So in other words, if f is a bounded function, then you have to be careful about the nature of fn's, because this is no more going to be a step process. But I know that I can really break it down to the step process as well, because each of the fn's, okay, is of this type, and for each of the fn terms in the sequence, I can find a step process that can approximate it. Okay, so everything boils down to the same step processes. So that's what we defined rigorously mathematically. Okay? Now, what I would like to do And then we did one example quickly. I mean, you can go through those examples as well, that how to, compute the, some examples of a stochastic integral, okay, using, really that process. And basically, we can also see that, this L2AD is obviously non-empty because Brownian motion, belongs here. It satisfies the definition. It's adopted by definition. And the expectation of w.r.t is going to be t, which is Riemann integrable as well. So, there are many functions which are there. In fact, you can also observe that the square, all square integrable function, okay, are also here. Okay. Why they are here? Because being deterministic, they are measurable always, and the expectation of f square of t for the deterministic function is basically f square of t, which is finite by definition for each such functions. Anyway, so we should have this coherent picture in our head actually. If you want to piece ahead, none of these fundamental pieces should be missing actually. All right, so now let's move to a bit more detail. The next thing that we can say that, I know for the case where we define, say, the stochastic integrals or Wiener integrals for deterministic functions that are square integrable, that a stochastic process defined by or induced by the stochastic integral or the Wiener integral is a martingale. Okay. The question is, can we have something similar here? In other words, if you take an arbitrary process, okay, process f from L to AD, and by the way, L to AD is defined on this cross product of omega and dRA to be omega. Question is, if I take an arbitrary process from here and define a process, I know that and I take this stochastic integral, say a to an arbitrary instant t, okay, f of t dw of t, I know that it's well defined because we just defined it for any instant t, a to b, and I can give this guy a name, md. Okay. The claim is that this process is a martingale. Okay, so the process defined by a stochastic integral is a martingale with respect to which filtration? The underlying filtration ft. So never forget assumptions of t. Okay. So think for the rest of the quantities, the rest of the arguments for yourself, that I'm going to only focus on the martingale property. Okay. So the why martingale property is true. I'll just give you a brief description, not too much detailed argument. So what I would like to show, so what would be I would like to compute expectation of MT given Fs, where f is some instant before t. Okay, that's what I would like to, prove to be ms almost true here, be almost true. Okay, but I can break this mt into say ms plus the integral from s to t f of u n. You can always break it like that. And if you want to compute, say, conditional expectation of MT given Fs, I need to show that, this is fine because Ms is Fs measurable, okay, and so it should be F plus, like this is obviously a fact that must be verified. For the martingale-ness. S to t f of u given fs. Okay, so this is going to be the case. So if I can show that this guy, okay, is a 0, P almost surely I'm done with the proof. Okay, that's what I would like to show, that this must be T. Now, F is an arbitrary process under 280, so I can always find a sequence of a step process, okay, Fn, that approximates the F in L280 sensor. Okay, in L280 sensor, that's what approximation limit is. The interesting thing would be that, okay, if in this expression, if I replace F by, for example, Fn's, okay, would that be 0 actually? Okay, so what I would like to show? So I would like to show this. As Fn converges to F, okay, as n goes to infinity, I'm going to show that the conditional expectations of Fn's dw given Fs converges to conditional expectation of F dw Fs as n goes to infinity. And I'm going to show that if I have the conditional expectation from S to T of Fn of dw of u given Fs must be 0, and hence the conditional expectation must be 0. Okay? That's what is going to be really the crux of the argument. So let's see that why this guy is true. Okay. Why this is true. By the way, I can write it a bit more precisely for the sake of simplicity, that this means that limit n goes to infinity, integral of a to b of a fn of u minus f of u squared dt goes to 0. Okay, that's what precisely that n goes to infinity. Okay, that's what it is going to mean if something converts into 80. Okay. Now consider a process xt, okay, relevant to an index n, and this simply means that integrate, okay, from a to t, okay, this fn of u and dw. Okay? Let's define this map. Then I know that this xt with, you know, index n can be written as xs with index n plus s to t fn of u dw. Okay, good. Anything interesting? लिख सकते हैं? Now, if I take the arbitrary increment of mt and ms, mt and ms, can I say that this would be same as mt minus, say, xt n plus xt with index n minus ms. Okay? Take it. Just adding, subtracting a bit. And the conditional expectation of mt minus ms given fs is going to be equal to, okay, conditional expectation of mt minus xt and given fs plus conditional expectation of xt n minus ms given fs. This would be the. Now I would like to actually this being, so let's see that. This is also going to show, okay, so, another trick could be that I just show that this side goes to 0 p almost surely. That would also prove the martingale equality that is required. Okay. Now, can I say, so here's the thing. So I would like to apply this conditional Jansen's inequality. Jansen's inequality for the conditional expectation would simply say that if you have a convex function and say phi of x conditional expectation of x given g should be same as can be estimated by the expectation of phi of x given g. Okay, and I would like to apply this conditional expectation property for x squared, which is obviously convex. Okay. So if this would be the case, I can say that expectation of xt by d minus xt n is squared. Okay, not squared, but everything is squared can be estimated, okay, by the expectation of mt minus xt and the square given fs. Okay. Alright? And this would be still true if I say, for example, take expectation on the both sides as well. Okay. Now this is the expectation of the conditional expectation. So the expectation of the conditional expectation is simply expectation actually. So I can say that this would be equal to expectation of t minus xt with index n squared. Okay. That's one of the inequality. And observe another interesting thing, that I can play the same game, a similar kind of an inequality for the expectation of xtn, xt, but what would be this actually? I mean, okay. What would be this? So this would be isometry. I can apply isometry here, and I can say that this would be same as the Riemann integral from a to b, okay, of mt, okay, which is expectation of mt by integrand जो है it's f of u minus fn of u का square, okay, and dt. Okay. So you could write this as, this answer. ठीक है, समझ आ रही है? So the expectation of I of f, which is a stochastic integral, so that's like a stochastic integral, and it's a square, is equal to the Riemann integral of the expectation of the integrand's square actually. Okay? Really, the isometry. Okay? I'm using this isometry. Expectation of I of f square is same as a to b expectation of the integrand square dt. So that's precisely what we are saying actually. Okay? And what do I know something about it? Okay, not a to b, not a to b. Okay, you can say this should be a to t actually. It should be a to t, not a to b. But I can estimate this by the same but a to b. Okay, I can estimate this by a to b because the integrand is non-negative, and then I can say this goes to 0 as n goes to infinity. this goes to 0 as n goes to infinity. Okay, so this shows that this goes to 0 as n goes to infinity, but there is nothing difference between this and this, so you can also show that this also goes to 0 as n goes to infinity. So you have the martingale method, the martingale property.